Thank you for the introduction. So yeah, today I'm going to talk about our recent work that we're going to present at UAI this summer. This is joint work with Paddy Denori, Nikolai Malkin, Doina Prikap, and Joshua Benjamin. So the problem setup is that we are interested in doing probabilistic inference. So this is a very, very general problem. But for us, what this means is that if we're given a fixed energy function, so this energy function E, then we want to sample from the Gibbs distribution, which is exponentiated energy normalized by some partition function. So this is really the only problem that we're interested in this talk. And why is this an interesting problem? Well, when you want to do probabilistic inference in general, then you need to compute all sorts of expectations of some functions. And this, if you want to use a Monte Carlo estimation, then this requires sampling from these distributions. So really, at the core of these problems of everything that has to do with inference, we need to tackle this problem of sampling.
Yeah. Just to be sure, so your main goal is not going to be just sampling sample, but just estimate like this.
No, so it's only sampling. We're not trying to compute what's the probability. It's really just sampling. And this is like it seems to be an easy problem, right? We have a distribution, just sample from it. What could go wrong? So the issue is that we have a partition function, this normalization constant z, which is in general intractable, and especially in the problems that we'll be interested in, which are problems where we have a discrete sample space, and this sample space is going to be combinatorially large. So if you want to compute the partition function, then it requires summing over a very, very large number of objects, and this becomes completely intractable. So this will be the setting in which we're in, but we still assume that it is a discrete and finite sample space. And another assumption that we're going to make is that the objects that we're going to consider, they have some kind of structure. And we'll see some examples of that down the line, but the key idea is that they can be constructed piece by piece. We'll see an example of that. So to give you a very, very simple example, let's take a language modeling example. This is very popular these days. So let's say I have this prompt, which is what should I do this weekend? And then I can have a bunch of different continuation of this prompt, depending on what are my preferences. So I have, for example, playing board games, baking cookies, playing footballs, and so on. And then for each of them, we assume that we can compute what's the energy function, what's the energy associated to this completion. So that's the energy function E, and it's a little bit counterintuitive, but if the energy is high, then this is something that I don't necessarily want to do. So for example, working on my rebuttals, this is something I don't necessarily want to do during my weekend, so it will have a high energy versus playing board games, which is going to have a lower energy. And the energy can be anything, really. It can be a positive or a negative value. In the end, what we're going to use it for is going to be exponentiated, so everything is going to be. So I have all of these different outcomes, but and I can treat them as being independent outcomes from one another. But another way to see it is by treating that as an autoregressive problem. So we start from nothing, which is the end of the prompt, and then I can see it as adding one word at a time. And so this is going to be the kind of structure that I was talking about before. Here, the structure is just going to be, I have a partial sequence, and then I'm going to add a word one at a time. And so we can see that this creates some sort of tree where at the end, at the leaves, we have the complete completion of the prompt that we started with. So at the end of each of them, we'll have the energy function associated to each of these completions. So this is really the one way to see it. Another way so just to remind everyone, I'll keep that on top just to make sure that we all remember what's the objective. The objective is just going to be sampling from this distribution defined up to a normalization cost. And so another way to see that is from the reinforcement learning point of view. So we'll assume that we have a finite horizon and deterministic MTP. So here, all of the states, all of the nodes in this tree that we had earlier, we can treat them as states in a Markov decision process. And then the states, they are going to be potentially partially constructed objects. So we don't just look at what's going on at the outcome with the complete completions, but we'll look at every single steps in between when we partially construct these sequences. And then at the end, we have a special state which is called SF here, which is a little bit small, but which gathers all of the complete completions that we ended up at. So it's really the same thing as the tree that I presented before. It's just we added this extra state to indicate that we're terminating the generation at this stage. And so the complete objects that we end up with, these complete sequences, we call them terminating states. This is just terminology that we'll go back to a little bit later. And then an action in this MTP is just moving from one state to another, and this is a deterministic process. And this just corresponds to adding a piece to the partially constructed object that we consider here. It's just adding appending a word to the state that we're in. And then the only thing, so this is like a very general setting. The only thing that we require is to know how we are defining the reward function. And the reward function, we're going to define it in a very particular way, in such a way that if we sum the rewards along a certain trajectory, this is going to be equal to the energy function at the terminating state at which we end up at. And so, for example, this covers a setting where we have a sparse reward. So we receive a reward of 0 at every stage of the generation. That we only receive the minus the energy at the end when we move from the terminating state to the state SF. This is what I'm showing here. But there are other ways we can define the reward. The only thing that we require is that it satisfies this condition over here. So this is important. So I will keep the reward, the definition of the reward, also on top so that we don't forget about it. So this is the definition of a Markov decision process. And so what we can do with it is just apply any kind of reinforcement learning algorithm on top of it. So recall that the problem of RL is to find a policy that is going to maximize the expected sum of your warrants. So it's to find this policy pi star that is maximizing this expectation. And then if we look at that and we take the definition of the reward that we saw before, this only says that we want to find a policy that is going to lead us to a terminating state that is going to have the lowest energy, because the sum of reward is going to be minus the energy. So if we maximize this, it means that we're minimizing the energy. And if we go back to the objective that we had earlier, it doesn't mean that we are going to find a policy to sample from this distribution, but it's going to find a policy that is going to find the mode of the distribution, just the one state that is going to have the highest probability. So this is not quite what we want. Just RL by itself is not quite what we want. We don't want just the single single terminating state with the highest probability. We want to be able to sample potentially under like suboptimal terminating states as well. So another way to see that is to treat this as a maximum entropy RL problem. So maximum RL problem, it's very similar to what we saw before. But instead of just maximizing the sum of reward, we are going to add some regularization based on the entropy of the policy. So the idea is that we don't want to find one policy which is always going to find the maximum, the terminating state, which is going to minimize this energy. We want to also encourage some kind of diversity in terms of the terminating states that we're seeing. So this is the problem, the optimization problem that we're solving. It's just regularized RL. And then from the control as inference literature, we know that we know the form that this optimal policy is going to take. This optimal policy is going to satisfy the fact that if we take the policy of a complete trajectory, so starting from the initial state and going all the way to a terminating state, so it's just multiplying the probability of each transition under this optimal policy, then we know that this is going to be proportional to expectation of 1 over alpha, the sum of reward. So again, if we take the reward that we were considering before, the sum of reward is minus the energy of the terminating state, and so now we have a way to if we know the optimal policy under this maxent RL problem, then we have a way that we can sample from the Gibbs distribution, which is what we were originally trying to do. Yes.
Alpha is a hyperparameter.
Exactly. So alpha is a hyperparameter, and this alpha that appears in the objective of maxent RL is exactly the same as the alpha, the temperature parameter that we have in the Gibbs distribution. So there's all these things.
Yeah. So just to shout for non-expert area, like the expectation of a price, like the action, I guess, which
yeah, so think not the expectation over actions. Think about it as an expectation over trajectories. So you're running the policy. So you start from the initial state, then you run the policy, okay, and then this creates a bunch of trajectories. And then the expectation is going to be over these different trajectories that you're taking.
Okay, because like there's an upfront about pi and expectation about pi.
So it's an expectation over trajectories sampled.
Okay,
yeah. So it's like the notation is a little bit like shortened. Yeah. But this is an expectation of a trajectory.
Okay, so each trajectory gives you like sum of reward.
Exactly.
Expectation of sum of reward.
Exactly. Yeah. So that's it. It's the shortest presentation ever. Like we have a way to we just solve maxent RL. And then we have a way to get a process that samples from the Gibbs distribution. Well, it's not quite as simple as that, and the reason for that is this distribution here, which is proportional to what we want in the end, exponential of minus the energy. This is a distribution over trajectories. But what we want is a distribution over terminating states. So we don't really care about how we get to a terminating state. We care about which terminating state we end up at. And so when we look at this particular example where we have a tree essentially, then this doesn't really matter because we only have one single way that we can go to any possible terminating states. But really what we care about is what we call this terminating state distribution, which is just the marginal over all the trajectories that will end up at a particular terminating state x of this pi star of tau that we have. So as I said, this is really not a problem when we talk about trees. But let's take this other example of molecule generation. This is a very toy molecule generation example where we're constructing a molecule by adding one fragment at a time. And so here we only have three different terminating states and 4 different complete trajectories. And notice that we have this terminating state x4, which has 2 different trajectories that can lead to it. There's this, I don't know, like COOH component that is added first, and then this hexagonal component which is added first, and then like we can create this molecule that we have at x4 by either adding one fragment and then the other, or the other fragment. And so here, if we consider that, and then we take what's the this optimal policy under maxent RL for each different trajectories, then we know from what we saw from control as inference is that it's going to be equal to exponential of minus the energy. And then when we want to marginalize over the terminating states, then we end up with some kind of bias for the terminating state x4 because we're summing two different trajectories going to x4. So this does not match the Gibbs distribution that we want because we don't want to have this two in front of it. So the key question is going to be how can we, like, what can we do to remove this bias eventually? So so one way to solve this problem, like an alternative way to have a process to sample from the Gibbs distribution is something called generative flow networks or GFLOWnets. So I already presented things about GFLOWnets last year, but just as a reminder, so the objective is exactly what we said before. It's to sample from a distribution over discrete and compositional objects. And we're going to treat this generation, again, as a sequential decision-making problem, starting from an initial state. And then now, instead of doing this RL avenue that I was describing before, here, what we're going to try to find is not directly a policy, but it's going to be a flow function that is going to satisfy what we call these flow matching conditions, which just says that, so the flow is going to be at every transition in this MTP. At every transition, we're going to have a certain flow function. And then the flow matching condition is very intuitive. It just means that the total amount of flow going into any state is going to be equal to the total amount of flow going out of the state. And then in addition to that, we'll have this boundary condition, which is that at every terminating state, the flow of terminating going to the terminal state SF is going to be equal to exponential of minus the energy. And so this is very quickly what GFLOWnets do. But what's crucial is that if the main theorem that we have in GFLOWnets is that if the flow matching condition and the boundary conditions are satisfied, so all of these two conditions that I presented before, then if we define the policy as just being the flows normalized by the total amount of flow going out of any state, then we can generate samples from the distribution, which is the target distribution that we started with. So really here, we found a way to define a policy in such a way that following this policy, even if we are summing over different ways, different trajectories leading to a certain terminating state, we'll still get something which is proportional to exponential minus the energy and not having the number of the number of trajectories appearing in this distribution. So we have a way to solve the problem that we were interested in, which is sampling from the Gibbs distribution through generative flow networks. But now the question is, can we achieve the same thing with Max and RL? Because Max and RL, we saw that we were very close to solving the same problem. The only issue was that in cases where we had multiple trajectories going to a certain term. And so it turns out that we can. And so this is something that we're showing in this paper, and some other concurrent work I've been looking into as well, which is that Max and RL. So what we saw before is that Max and RL was giving us a terminating state distribution, which was biased towards states with multiple paths leading to them. And so if we were choosing the definition of the reward as being the sum of reward is equal to minus the energy, and we were applying Max and RL, then we were ending up with terminating state distribution, which had this term n of x appearing, n of x being the number of trajectories leading to x. So this is not quite what we want. But then what we show in the paper is that instead of completely changing everything and moving to GFLOWnets, what we can do is just apply Max and RL to a different MTP. And this different MTP is just going to be changing the definition of the reward function. Just going to correct the reward function to add something that we call the backward policy. So instead of being just the sum of reward being equal to minus the energy, Now we also want to add the sum of backward policies to the definition of this reward. So what we show in the paper is that if we define the MDP with this reward function and we apply maxent RL, then we end up with an optimal policy, and with an optimal policy whose terminating state distribution is going to be proportional to exponential minus the energy, which is precisely what we want to do. And just it might seem a little bit weird, like what's this PB? PB is really just, you have to think about it as being just when you're in a certain state, this is a distribution over the parents. So instead of being a policy where you're in a state and then this is a distribution over the children, here it's a distribution over the parents. And this works for any kind of backward policy that we can think of. So usually you can take, for example, the uniform policy, the uniform backward policy, which is taking 1 over the number of parents, and this will still work. So yeah, any questions for that?
Yes, maybe just for the backward policy, because before you had the policy, so it was clear, I guess, from an algorithm point of view, you try a policy and then you update the backward policy.
So this is a fixed, this is
Oh,
fixed.
it's fixed.
Exactly.
Okay.
So that's one thing. So this is, we consider this to be fixed.
It's not learned.
The only thing that we're learning is the forward policy. This is still this policy pi that we're learning. This is just a fixed thing to correct things down the road.
But, so you have to assume that you know the like optimal backward policy.
So it's not optimal backward policy. It's it works for any kind of backward policy. So no matter what's the backward policy, this will work. And so you can fix like a backward policy to, in most of our experiments, we're just fixing it literally to the uniform distribution over parents. And this works.
And you still have the result that pi star is good.
Exactly. Yeah. For any backward policy, this works. And so the reason for that is that if there is a result, which is that if you sum over multiple trajectories going to a certain terminating state, the product of backward policy this time, this is always going to be equal to 1. So the backward policy induces a distribution over all of the trajectories going to a certain terminating state. So here, essentially what we're doing is, instead of having a sum in the definition of the terminating state, which is the reason why we have this number of trajectories appearing, we're transforming that into an expectation. And the expectation is going to be taken with respect to this backward policy. This is not important sampling though, because you don't. So nowhere in here you have like an important sampling ratio.
You're like aiding this decisional firm to account for your backward policy.
Yeah.
For expectation. I mean, it's not like implicitly the density ratio appears, but the principles. Or taking the expectation over some like simple distribution, and then we'll take this into account and we'll report it. So like it's kind of like
the thing. So what you mean is that when you, so if you look at this expectation over pi, which is an expectation over trajectories. So the thing is, these are two different spaces in a way. Here, when I say that PB defines a distribution over trajectories, it's a distribution over trajectories, or like ending at a certain terminating state. So you fix the terminating state, and then it's all the trajectories leading to that. For the forward policy, what we have is that the distribution over, like the forward policy is inducing a distribution over all of the trajectories, no matter where they are going to end up. So these, like, there's a mismatch between the space of the space over which the forward policy is going to induce a distribution, which is all of the trajectories.
yeah,
And PV is like just the ones that are
the condition will be
Yeah, but also at the endpoint, what's the distribution that you started with? Like if you talk about importance sampling, there is like this correction, like this PB, which is going to be the correction. But what was the initial distribution that you started with?
Right.
So when you're talking about importance sampling, you have the policy with respect to which you're taking the expectation, and then there's a behavior policy. So here, what you're suggesting is that the behavior policy would be this. Okay, so what are you? Maybe I did not.
Maybe like, okay, so like it's just like, yeah, I think it's not really abstracted. But like importance sampling appears in different ways, and I'm not very sure what people refer to importance sampling in like reinforcement learning. But in general, when you like, I think that if you say that, okay, you have to, your expectation is invariant over the factor policies, and there is something in that is like importance sampling, maybe implicitly, but essentially you're reweighting your paths.
Exactly, you're reweighting your.
Exactly.
That's true.
So
Right?
that's what people call importance sampling, whatever. And you can like, for example, you can take a look at different instantiations of this where like people, for example, to importance sampling over like trajectories in the Riemann path formula. We like sample from one distribution and then reweight, and it is kind of like importance sampling. It is not like, I think you took my words too literally in the way that like, oh, this is like importance sampling in RL or like importance sampling in Montréal or the basis ratio.
Yep.
It's just in general what I meant that like when you like sample over one distribution and reweight your trajectories, this is like importance sampling.
But here you're not taking expectations anywhere. What we have is just the distribution. So it's so you could imagine like, okay, what am I going to use it for later on? This is what I had in my first slide where I said you can use the Gibbs, like samples from the Gibbs distribution to estimate expectations with Monte Carlo. You can maybe think about it in this way, but it's a bit, I don't know. Like, I think it's a very, very tenuous correspondence.
Go first, man. We can discuss it.
Absolutely, yeah. Yeah. Any other questions on this thing? So this is something that was also found in by other people in other groups. The fact that you can correct the reward in such a way that involves this backward policy to correct this bias induced by multiple trajectories leading to a certain terminating state. But their setting was specifically for the case where you have a sparse reward where the energy was only received at the end. Then you were adding log PB at every stage of the generation. So here, instead of receiving a reward of 0 at every stage and then only minus the energy at the end, then after the correction, you can add alpha log PB for each transition, and then still receiving minus the energy. So this was the case that was considered before. One thing which is interesting is that what I showed you before at the beginning is that when we had a tree, then just using max and RL was doing exactly what we were expecting to do. And we were getting the samples from the Gibbs distribution. Well, this matches exactly what we have here, because in the case of a tree, every state only has one parent. So any any backward policy is going to be equal to just 1 for this one time that it is. So we recover the case where we had an uncorrected reward. And then there is another work coming from Pierre-Luc Vacquin's group at Mila, which is very similar to that, but they were considering the case where the backward policy had this particular form where n, again, was the number of trajectories leading to a certain state. And then if they were using that, they showed that you get a policy which is maximizing the entropy over trajectories. So this is an interesting special case of this result as well. So this is things that were existing in some very recent works as well. What we showed in the paper using this correction of the reward that I showed you before is that many, if not all of the objectives that were introduced in GFlowNets over the past few years, they find an exact equivalent in the MaxEntRL literature. So it's really just exactly the same algorithms, exactly the same objectives. The only thing that differs is the way that we're defining the reward function for MaxEntRL. So just to give you a few examples, I'll just highlight these two correspondences. So between path, like an algorithm in MaxEntRL called path consistency learning, and this sub-trajectory balance in GFlowNet on the one hand, and then on the other hand, the correspondence between the soft Q-learning algorithm in MaxEntRL, which is probably the easiest algorithm that you can think of to solve MaxEntRL, and something called the forward-looking detail balance, which was introduced. So yes.
So I have multiple times that GFlowNet is MaxEntRL regular.
Yeah, exactly. This is exactly the same thing. Like MaxEntRL, GFlowNet, they're like two faces of the same coin. Really, that's one way to see it. I'll briefly touch on that at the very end to say that it's not the end for GFlowNet. There's still a lot of things that can be done, but really you can think about it as really being the same thing. And in terms of objectives, in terms of algorithms, sorry, these are really.
So when you're saying it's the same thing, that means produce the same output formulation, or it's just another notation, but
it's the same objective. So the objective that you're solving is really the same.
Okay.
So let me show you like one example, for example. So this equivalence between path consistency learning and TB. So path consistency learning, this is a MaxEntRL algorithm that is encouraging the consistency at the level of complete trajectory. So if you look at complete trajectory, and then you look at what's going on between the values at both ends of these trajectories and the policy, then you have this consistency that we're trying to encourage, which is what we show in this delta PCL. This is on the one hand what we have for MaxEntRL, and on the GFlowNet side, we have this objective which is very popular called trajectory balance, and it also encourages some kind of consistency at the level of trajectories. And then the objective that corresponds to it is given by this delta sub TB that I show down there. And then the objective for both PCL and trajectory balance, we can write them as just a least square objective involving these residuals that I'm showing over here. So if you write down the objectives for PCL and the objective for sub TB, they are going to be exactly equal up to this hyperparameter alpha, which is going to appear here. But really, both of them are going to be exactly proportional to one another. And there is a way to move from the MaxEntRL formulation to the GFlowNet one and back to. So what we call the policy in MaxEntRL is also the policy in GFlowNet. And what we call the value function, the state value function in MaxEntRL is what we call the flow in GFlowNet. But really, there is a one-to-one correspondence between the two. So this is really interesting because it just means that instead of using sub-TB, we can use path consistency learning on this just corrected MDP. And so this equivalence was in the case where we have a very specific definition of the reward, where it's still a sparse reward that you receive at the end. And so after the correction, we're just receiving alpha log PB along the trajectory. The other equivalence that I want to highlight, which is something that was not possible with prior work, is this equivalence between soft Q learning and forward-looking DB. And the idea is that instead of so far we only considered cases where we received the energy only at the end of the trajectory, but the condition that we had initially was just that the sum of reward was equal to minus the energy. And so if we have an energy function which has a very specific structure, which is that it can be broken down into a sum of little pieces that you can get along the way, then before the correction, you can think about having an MDP which is receiving these little pieces of energy along the way. And then if you sum the rewards, it's going to be exactly minus the energy. But then after the correction, we can do exactly the same thing and add alpha log PB to every single of these little pieces that we acquired along the way, and having a zero reward at the end. And then using this definition of the reward, what we show is that soft Q learning, which is the Max-Centaurel counterpart of Q learning, given by the residual on top here with delta SQL, this is going to be exactly equal to the forward-looking detail, the objective for forward-looking detail balance, whose residual is given by delta FLDB. So we have really the same result as before, which is that the objective for SQL is going to be proportional to the objective for forward-looking DB, the multiplication constant being just the temperature parameter alpha. So these are like just two different relations between Max-Centaurel algorithms and GFloNet's objectives that I'm going to show here. But in the paper, we show all of the other correspondence that I presented. So in terms of experiments, so the experiments that we ran was just to validate the fact that these objectives really achieve the same thing. So our objective was to run different GFloNet algorithms and Max-Centaurel algorithms, and then see that see these different correspondences between algorithms where the basically the loss functions would match exactly one another. So I'm going to talk about this experiment on discrete factor graphs. So suppose that you have a discrete we have a discrete factor graph with a known structure and a known factors. So one example of a discrete factor graph is what we have in the middle, with x1, x2, and x3 being random variables that are connected through factors psi1, psi2, and psi3. And then each variable can take a value between, so this is a discrete random variable, so it can take a value between 1 and k. And so this makes the sample space exponentially large, which is the setting in which we were placing ourselves at the very beginning. And the way that we're going to treat that as a sequential decision-making problem, to see that from the point of view of an MTP, is that we're going to assign the values of the random variables one at a time. So we start from the very beginning where none of the variables have a value that is being assigned. And then at the first step, we're going to assign one value, but not necessarily the first one. It can be the second one or the third one. And then at the second stage, we're assigning another value of another variable. And then the third stage, we're assigning the last variable that we end up at. And then the energy function is just a fixed function, which is given by, so for this particular this particular factor graph, the energy function is just going to be the sum of different factors, which are known functions. So we have a way to compute the energy function. We have this oracle that can compute this energy function. So that once we reach a terminating state, we can evaluate this energy. So these are results. These are learning curves for different settings that were considered in the literature before. So on chains, permuted chains, and different structures of factor graphs. And so what is interesting is that if we look at the different learning curves, is that SQL and detailed balance, so software learning and detailed balance are exactly matching in terms of learning behavior. Same thing for PCL and DB. We have learning curves that are exactly matching, which is what we were expecting. It matches the theoretical result that we had initially. Something which is interesting is that, and we experimented with it, is that we also considered another algorithm from the Max Centaurel side, which is called soft actor predict, which has no counterpart in GFONet. And we found in this particular example that soft actor predict, which is very popular in RL, does fairly well on this problem of factor graphs, but there are some other cases where it can also underperform. So there's still a lot of things that can be explored in terms of applying really purely Max Centaurel algorithms to these problems of probabilistic inference. And then in the paper, we also have some other experiments that I won't have time to go into to the details here, but we have some experiments on using that for Bayesian structural learning, so learning the structure of a Bayesian network, and also phylogenetic tree generation. So if you have a number of species and then trying to find a distribution over the different phylogenetic trees that are relating these different species. So these are in the papers if you are interested as well. But what we found consistently is that the algorithms that we were expecting to be that we showed were exactly equivalent to one another have the same performance down the line in terms of either learning curves or the performance that we get. So I'm going to conclude with a few thoughts. One of them is that this correspondence between GFONets and Max Centaurel can, in some way, explain all of the bags of tricks that we've been using from the reinforcement learning literature, and we transfer it back into GFONets. So a lot of things have been borrowed from the RL literature. So, for example, replay, the notion of replay buffers, target networks, the distributional view of distributional RL, and also some advanced exploration strategies. These are all things that were only introduced by taking inspiration from RL. But what we show is that since these two things are exactly the same thing, what we have in these works is not really surprising, because they're really all of the tricks that we should be using in GFONets, because it's exactly the same. So now the question, to go back to what I said before, is it the end for GFONets? Because if all we're doing is just Max Centaurel at the end of the day. So the answer is not quite yes. And the reason for that is, recall that all of our theory was based on the fact that we were correcting the reward function of the MDP based on a backward policy. And then I said that this could work for any kind of backward policy. This is true. It can work with any kind of backward policy. But the thing is, it still has to be a fixed backward policy. So we're not learning this backward policy. This PB here is not this is something that is fixed once and for all. And we shouldn't, we don't touch it. But in terms of GFONets, PB is something that we can learn as well. And in some cases, it has been shown that if you learn PB, you find better solution of your problem. So it makes optimization easier to learn PB. But if you view that from the point of view of Max Centaurel, since PB appears in the reward function, this is not something that you can easily learn along with everything else. If you treat that as being a learnable component, then you end up with something which is akin to inverse reinforcement learning, and this becomes a lot more challenging. This is something that is not as easy. So just from a framework point of view, this is not exact. This is like learning PB is not possible in Max and RL. In terms of implementation, you could learn PB. It's in terms of implementation, GFloNets and Max and RL, they are really similar to one another. So there is nothing that is preventing you from doing it just in practice. But in theory, there is this mismatch between the fact that in RL your reward needs to be fixed. You cannot learn this. So that's one advantage of GFloNets. It's we don't need to change the framework to make it so that PB can be learned. It's just handled by this. So that's why I think there's still value in looking into GFloNets even with this. And then finally, this is something that is not in the paper, but this is something that I've been looking into recently. This is interesting. So far I've been talking about the problem of entropy regularized RL. So what we were doing is taking the objective of RL and then adding an entropy regularization on top. But recently, what has been very popular, especially with RLHF, is instead of using just a regular entropy, is to use a relative entropy. Is having a KL penalty between the policy and some behavior policy, which is. And so if we, what's interesting is that if we apply the same techniques that we were using in the paper to show with the correction that we were ending up at the Gibbs distribution that we cared about at first, we can use exactly the same proof. And what we can show is that if we are in the same setting as I talked about at the very beginning, so the uncorrected reward without any of this log PB or anything like that. If we're finding the optimal policy that is maximizing this KL regularized RL problem, what we find is that the terminating state distribution for the optimal policy is related to the terminating state distribution of the behavior policy U and times the exponential of minus the energy. And so in itself, it's not necessarily very interesting. It's just like a way to relate two different terminating state distribution with this added exponential of minus the energy. But one particular application that I'm really excited about is the application for Bayesian inference in general. Because what we have in Bayesian inference, what we want to find is a way to sample from the posterior distribution, this P of theta given some data set. And this thing is proportional to the prior times the likelihood. And now if we find a behavior policy mu in such a way that its terminating state distribution is equal to the prior, and then if we define the energy function in such a way that exponential of minus the energy is the likelihood, then we can find a policy pi star whose terminating state distribution is going to match the posterior distribution. And so this gives us a recipe to do Bayesian inference. What we can do is that we can find this behavior policy mu that is going to match the prior. So for that, we can use, for example, the GFloNet or some of the techniques that we talked about with Max and RL. And then once we have this policy mu, which is fixed, then we can solve the problem with the KL regularization and the energy function, which is defined in such a way that its exponential is the likelihood. And then what we get at the end is something which is going to be match the posterior distribution. So all in all that to say that this gives us, like, it's usually going to, like, we are sidestepping some of the difficulties. If we were to do it just in one go learning all at once this posterior distribution. Sometimes it can be very challenging because the energy function is going to be vary a lot because of the data. But what we can do is just sidestep some of this complication into learning this behavior policy at first, and then trying to get this posterior distribution a little bit in an easier way from an optimization to do. So this is something that has been also explored lately. So some of these results have been used in some work that has been done by some teams at Mila as well. So this is a promising direction as well from an optimization. So that's it. Thank you everyone for attending. Thank you for the questions. We have some code in JAX available there with all of the algorithms and all the different environments that we looked into. So if you're interested, feel free to check it out. Thank you.
Thank you to solve our story. So we have the time for just a couple of questions. Is there any question for Tristan? So can you go back to the slide where you did the experiments and show the graphs? Yes. So it's a bit quite surprising that with two different behavior, one for SQL and DP and the other for PCNet.
Yeah.
So could you imagine also something that would somehow combine the two regime where you converge quickly at the beginning and still have better end performance?
That is a very good question.
Also, do you know why it's
so I think the reason why it's behaving differently is that trajectory balance, like I'm going to talk about, that's just the G-fronted counterpoint. Trajectory balance is looking at what's happening at the level of a complete trajectory. And so if you think about it, we'll have to take the product of the policy all along the trajectory. And so in terms of training signal, we get the training signal for each of the steps along the trajectory. So effectively, when we're taking a gradient step with respect to this whole trajectory, it's kind of more information than just if we were looking at just what's happening at the level of the transition. And that's what DB is doing. DB is looking at what's happening just at the level of the transition. All right. So in terms of just the regime where it's going to perform better down the line, I think that's the reason why we're getting more more information from the grade, from back propagation, by looking at what's happening at the level, the whole trajectory.
Yeah, because at the beginning, since I guess it's random, that's why you do not get that much.
Exactly. Yeah. Exactly.
So that could be actually, I think, like an extra type of parameter, like how long you want to see the history to get the proof from.
Yeah. So this trajectory balance, the way that we were looking at that, it was looking at complete trajectories, so from the initial state to the terminating state. The result that we show theoretically, and what others have been looking into also, is to look at something which is a little bit in between these complete trajectories and just transitions. So they look at partial trajectories. So this is what we call the sub-trajectory balance. It's looking at really just what's happening at just some partial trajectories of a certain length, and sometimes it can help to look at that. That's true.
And then could be that it could be something that evolve over time, for instance, like it being just start very small and then
exactly. Yeah, this is something I can follow as well. So you can imagine doing it for transition at first, and then later on adding little by little. But there's also another option, which is to look at, if you only look at partial trajectories of length 3 bar, for example, then you can also look at all the sub trajectories of smaller length as well, because you're computing the probability of each transition anyway to compute this the probability of the sub trajectory. So you can also look at the consistency at the level of shorter trajectories as well. That's, I think, what people have been using as well.